Hi everyone. So in this talk, I'll discuss how we can use Monte Carlo methods to solve certain basic yet very fundamental partial differential equations in scenes with extremely complex geometry. And just like Monte Carlo methods for photorealistic rendering, I'll present simulation techniques that I believe can serve as powerful tools for a broader set of problems in science and engineering. So our basic motivating problem is the classic interpolation problem. We have some region with known values on the boundary, and we want to smoothly interpolate these values over the interior of the domain. Now this of course is the standard Laplace equation delta u equals 0 subject to Dirichlet boundary conditions, u equals g. So for folks who do geometry processing and simulation, we've traditionally been trained to think about solving such PDEs using a finite dimensional approximation. Here we first mesh the interior of the domain, then we use the mesh to define basis functions phi sub I, which we then use to compute a function u that satisfies our Laplace equation in a weak sense. But if we do things this way, then we'll necessarily have errors both due to the approximation of geometry as well as the approximation of functions. However, we can actually avoid a finite dimensional approximation completely by using Monte Carlo. So for a Laplace equation, this starts with Kakutani's principle, which says that if you want the solution at a point x, well, just take a bunch of Brownian random walks to the boundary, grab the known boundary value g, and then take the expected value. There's one problem though, which is how do we simulate Brownian motion? As you can probably see, a naive simulation of BM requires a lot of little discrete steps. So here we can observe that a random walk starting at x is actually equally likely to exit through all points on the sphere centered at x. So if we uniformly sample the sphere, then there's no discretization error at all. So this leads us to the walk on spheres algorithm, which solves a Laplace equation at a point x0 by taking the biggest empty sphere around x0, uniformly sampling the sphere, and repeating the random walk until it reaches the boundary. We actually have a bit of a Zeno's paradox of motion here because we never truly reach the boundary. But it turns out that it's perfectly fine to just grab the solution value from the closest point when we're within an epsilon distance to the boundary. Now, a completely different way to motivate this algorithm is through the mean value property of harmonic functions, which says that the value at any point is equal to the average over any sphere around that point. So if we repeatedly estimate the mean value integral using a single random sample, then again we get the same walk on spheres algorithm. And this duality between the stochastic and integral perspectives will be helpful as we go along. However, the walk on spheres algorithm, as I've described it, has one big limitation, which is that it only handles problems with Dirichlet boundary conditions, where boundary values are fixed and random walks are absorbed as soon as they hit the boundary. So in this work, we significantly expand the capabilities of walk on spheres by also handling Neumann conditions, where instead of interpolating fixed boundary values, we now need to interpolate derivatives. And as we'll see later in this talk, this will require us to simulate reflecting Brownian motion near the boundary instead. Okay, but before I go into any further details, I would like to first motivate why we want to do things this way. So the basic reason for seeking out alternative strategies to classic PDE solvers is that working with geometry through meshing can be really hard. But finding the closest point to the boundary, like we need for walk on spheres, is a simple and robust operation that doesn't really require any heavy data structures. And this is important because the geometry that we're dealing with today is only getting more complex as the years go on. We have extremely detailed data coming from laser scanning, shape optimization, computer vision, and text to 3D. But even after decades of working with methods for solving PDEs, we still struggle to handle the level of geometric complexity we find in nature. In fact, even state-of-the-art meshing tools can literally take hours to volumetrically mesh a single model. So if you're spending all of your time converting your domain into a mesh that's sim-ready, then it really doesn't matter how fast or accurate your finite element solver is. This issue is especially problematic because geometry encountered in the wild can be really bad, and such geometry is often the rule rather than the exception. Now, one approach is to keep improving meshing algorithms to handle degenerate inputs. And to be fair, these algorithms have gotten really good in recent years. But meshing and model cleanup more generally really seem like problems that will never be completely solved. Even with the latest and greatest tools, you run into situations where it can take hours to generate a tetrahedral mesh for a model with relatively simple geometry. And even if the meshing algorithm terminates, it can come at a cost, like missing important details, like vessels in a 3D model of the heart, that completely change the meaning of a PDE solution, modeling, for instance, oxygen or blood flow. A bad mesh can also provide a false sense of reality. So here's an example where we compute geodesic distances on a mesh with skinny triangles using a finite element solver. And notice that the FEM solution actually doesn't match the reference at all because of poor quality triangles. So back in the 90s, people ran up against the same problem in rendering. If you wanted to make a photorealistic image, you would use finite element radiosity, where you make a mesh of the scene, build a large linear system, and solve for illumination everywhere in the scene by inverting the linear system. Now, this idea fell out of fashion for many reasons, but in large part because robust meshing is just a really hard problem. So instead, the rendering community now uses Monte Carlo methods for estimating illumination that recursively shoot rays that bounce around the scene. So rather than meshing and global finite element solves, we now just have to intersect the domain boundary with a ray, which is both a lot easier to do in practice and a lot more robust to triangle quality. Beyond just being a beautiful idea, this shift to Monte Carlo methods has also really enabled modern photorealistic rendering, and it's had a major impact on industries like entertainment, industrial design, and these days computer vision, where we're really seeing leaps and bounds in our ability to reconstruct 3D objects from images. In fact, modern renderers have gotten so good that we can path trace factory scale scenes without any geometric preprocessing other than building a BVH, which is super fast to do compared to finite element meshing. And as it turns out, the distance queries needed by walk-on spheres can also be performed using a BVH. Now, of course, there are lots of other physical phenomena in science and engineering, such as thermal conduction, electromagnetism, and structural analysis, whose physics is different from that of light transport, and which at their simplest are actually described by Laplacian PDEs. So this is where I believe Monte Carlo methods like walk-on spheres can also provide a lot of the same benefits that we're seeing with rendering today. So for instance, just like with rendering, as long as the PDE we want to solve is well posed, we can be confident that a Monte Carlo solver will produce a physically meaningful solution. We don't have to know, for instance, what function spaces we're working with or what basis functions span that space. The cost of adding geometric detail grows like n log n, which means that we can scale to problems with literally billions of elements. So on the right, here we're showing a PDE with spatially varying material coefficients solved using walk-on spheres in a domain where the boundary mesh has over a billion instanced elements. And all of this is simulated without any kind of pre-processing. Just like with rendering, we get perfect parallel scaling by averaging the result from n different processors because we're basically just summing up independent Monte Carlo estimates. And we can immediately get a reliable preview of what the solution looks like by just taking a few samples. So on the right is a PDE being solved in real time in a shader program with walk-on spheres, again with no pre-computation. Just like rendering, we can work directly with a mix of different geometric representations like meshes or implicit surfaces without having to generate a separate sim-ready finite element mesh. And you get a totally reasonable solution even if your geometry has defects like cracks, self-intersections, and low-quality triangles. Just like path tracing, where you only render what you see through the camera, walk-on spheres lets you evaluate the solution only at points where you actually need it. And you're not forced to use Monte Carlo everywhere unless you want to. So in rendering, for instance, ray tracing is often used inside rasterization pipelines, and in principle, you could also use a Monte Carlo PDE solver somewhere inside a finite element simulation. Now, despite my excitement, I should say that there are all sorts of amazing simulation technologies out there where Monte Carlo may never be applicable. But given how far Monte Carlo has brought us in simulating realistic illumination, I think it's only natural to ask, well, can we build something like a ray tracer for problems beyond light transport that also scale to a really complex geometry? And so over the course of this talk, I'll provide examples in particular involving heat transfer and thermal conduction, where I think Monte Carlo PDE solvers are already immediately applicable and can even be combined in really interesting ways with path tracers. Okay, so let's switch focus again to how we can estimate the solution to Laplacian PDEs with Neumann boundary conditions. So these boundary conditions are fundamental for a number of very basic applications. In fluid mechanics, they provide the change in velocity or pressure gradient at an interface. In structure analysis, they prescribe the surface traction or stress. And in thermodynamics, they correspond to the heat flux across the boundary. So for instance, if the normal derivative was zero on the boundary, then that would mean that the Neumann boundary is insulated and heat isn't allowed to leave the domain. So now recall that the standard walk on spheres algorithm says that if we want the solution to a Laplace equation with Dirichlet boundary conditions at some point x0, then until we reach the domain boundary, we find the largest ball around the current point xk. We then sample the next point xk plus 1 on the boundary of the ball, and we keep doing this until we finally add the boundary value g at xk to our average. We then repeat this experiment n times to get our final estimate. But now what if I also have Neumann boundary conditions? And for simplicity, we'll assume that they equal 0. So then here's the algorithm, which we call walk on stars, which is actually conceptually very similar. So until we reach the Dirichlet part of the domain boundary, we now find a star-shaped region around a point xk. So this could be a ball, or more generally, it could be the intersection of a ball with the domain, like this one here. We then sample the next point on the boundary of a star-shaped region, and we keep going until we add a Dirichlet value to our estimate and repeat n times. So the key difference, as you can see in this picture, is that our random walks can now reflect off Neumann parts of the boundary. And this really is the right thing to do from a stochastic point of view, because Dirichlet conditions correspond to random walks that get absorbed, while Neumann conditions correspond to random walks that get reflected. So to develop an algorithm like this, we have to answer a very basic question, which is how can we efficiently simulate reflecting Brownian motion on domains with complex geometry? And the complex geometry is key because if you have simple geometry, like a random walk on a half plane, then reflected Brownian motion is nothing more than the absolute value of ordinary Brownian motion. Likewise, if you have a polyhedron with just a few faces, then reflected Brownian motion means that we can just reflect back across any face that we cross. So a naive idea is to just randomly sample the biggest sphere around X that crosses only a single edge, and then reflect back into the domain if we're outside. So the one big problem here is that this approach becomes super inefficient as the resolution of the geometry increases. Now, we could use a bigger ball and some heuristic for reflecting back into the domain, but if we do this, then we'll necessarily have error or bias because of the curvature at the vertices, which sort of negates the key strength of walk on spheres, which is that it simulates Brownian motion in an unbiased way. So another option is to just push a random walk back into the domain by a small fixed distance if it enters the epsilon shell around the Neumann boundary. So this approach has two serious problems. The first is that walk lengths can become extremely long since the boundary serves as an attractor for walk on spheres, which makes things extremely inefficient. The second is that we're effectively approximating the normal derivative using finite differences. So you get a large buildup of bias that accumulates with each boundary reflection. So to bypass these issues, the right answer is to return to the integral representation of our PDE. So recall that the solution to a Laplace equation has a mean value property over the ball, where we weight the unknown value u at y by 1 over the surface area of the ball. We can actually generalize this relation to consider sets other than just balls. So for any arbitrary subdomain A, the solution value at x now equals the integral of the Poisson kernel of A times the unknown solution values at all points y on the boundary of A. So think of this as a sort of generalized mean value property. So the next idea then is to take a walk on subdomains that can contain pieces of the Neumann boundary by just repeatedly sampling the Poisson kernel. And what you'll notice here is that we now have large steps that take us away from the boundary and which model reflections. But the problem is that to actually implement this strategy, we have to be able to sample the Poisson kernel. And unfortunately, this kernel is only really known for very simple regions like a ball or Euclidean space, but not for arbitrary regions A with complex geometry. Now, fortunately, there's an even more general version of this boundary integral equation that saves the day. So it says that we can pick any region A and any region C, and then integrate the Poisson kernel of C over the boundary of A. So this gives us a lot more options. So in particular, to derive the walk on stars algorithm, we let A be a star-shaped region, meaning a shape where every boundary point can be seen by the center point x. However, we'll just use the Poisson kernel of a ball, which looks something like this when plotted over a complex region boundary. Okay, so now why is this a good idea? Why use the star-shaped region of A with a Poisson kernel for a ball? Well, if we're standing at a point x, then the Poisson kernel at y equals the normal at y, dotted with the unit direction towards y, divided by the squared distance from x to y. Some of you might recognize this formula as the sine solid angle, which also shows up in the area formulation of the rendering equation. The sine solid angle is essentially the size of the shadow cast by a little piece of the boundary on a unit sphere around the point x, and it takes into account the orientation of the surface and the sphere. So this is really good news because to sample the Poisson kernel, we can just shoot a ray in a random direction to get our next walk location. So irrespective of whether we hit a piece of the ball or a piece of the domain boundary inside the ball, we're automatically sampling according to solid angle where we only ever have one intersection, which is really nice. Okay, so the final question is, how do we find big star-shaped regions which allow us to take big steps? So this turns out to be easy to answer as well. Rather than just taking the closest point, which is the only thing we needed for standard walk-on spheres, we now take the minimum distance to the closest point on the Dirichlet boundary and the closest point on the silhouette of the Neumann boundary, by which I mean the closest point where normals switch from front-facing to back-facing. Now, this might sound a little complicated, but we can actually compute the closest silhouette point efficiently using the same BVH we're already building for ray intersections and closest point queries. Basically, we just need to store a little extra information about normals that encode the orientation of the boundary, which we do by associating a cone with each bounding box in the hierarchy. Some of you might recognize this as the light BVH data structure used in ray tracers for next event estimation in scenes with many lights. Okay, so to recap, the algorithm is actually quite simple. We check if we're near the Dirichlet boundary. If not, we find the closest point and closest silhouette point. Then we shoot a ray at the corresponding star-shaped region to get the next walk location until we finally reach the Dirichlet boundary and we add to our total. We then repeat this process n times. Notice that walk-on stars automatically turns back into walk-on spheres when there's no Neumann boundary. This algorithm can be implemented in 150 lines of standard C++ code with no external dependencies, and if you want to see how, we wrote up a step-by-step tutorial on building this code up from scratch. We also have a reference C++ implementation with all of the additional features described in the paper, such as the treatment of non-zero Neumann conditions, where we now additionally pick up a contribution h with every reflection. There's also the treatment of pure Neumann problems, where we don't have a Dirichlet boundary to terminate on, as well as handling of open domains and double-sided boundary conditions, shown here in this example of a diffusion curves image with really intricate geometry. In this talk, we focused exclusively on the Laplace equation, but our method extends immediately to Poisson equations as well, and in principle to a much larger class of second-order linear elliptic equations with varying material coefficients, which are needed to model real-world physical systems that have complex variation. So in our 2022 paper, we actually showed that the stochastic integral formulation for these PDEs shares a lot of structural similarity with the volume rendering equation for the radiance L in something like a cloud or a puff of smoke. And we exploited this connection to adapt volumetric ray tracing algorithms such as delta tracking and next flight estimation to walk on spheres, where we developed estimators that are conceptually identical. Finally, another nice thing about walk-on spheres and walk-on stars is that we can estimate the spatial derivative of the solution basically free of cost. So things like divergence, curl, and directional derivatives. And in a second paper at SIGGRAPH this year, we show how to leverage these gradients to greatly reduce variance in PDE estimates computed using walk-on stars. Okay, so to validate our solver, the first thing we show is that it demonstrates the expected Monte Carlo rate of convergence for both its solution and derivative estimates. Now, another nice thing about walk-on stars is that it only has two parameters that don't really require much tuning. So on the Dirichlet boundary, the only parameter is an epsilon tolerance that specifies how close to the boundary we have to get before we grab the known boundary value. And in our experiments, we noticed that this tolerance introduces minimal bias and basically has the effect of extending the boundary conditions into a small neighborhood near the boundary. Also, unlike tolerances in meshing algorithms, the epsilon shell has little impact on performance. Near concave parts of the Neumann boundary, the size of a star-shaped region shrinks because the distance to the closest silhouette point goes to zero. So to prevent walks from stopping, we currently impose a minimum radius on the size of the ball, which, like the epsilon shell, comes with a performance and bias trade-off. But the main thing to point out here is that the size of a star-shaped region is actually typically much larger, even slightly away from a concave boundary. And in practice, we can use local curvature estimates to set this parameter adaptively, which would result in larger balls and faster runtime performance. Compared to other Monte Carlo algorithms like the walk-on boundary method, we find that walk-on stars does much better both in terms of variance and bias as we have more and more reflecting boundaries. One could also try to simulate Brownian motion using standard SDE integration schemes, but this actually tends to produce extremely biased results and is also very slow even in domains with relatively simple geometry because of small step sizes. In comparison, walk-on stars takes large steps and introduces negligible bias. For problems with complex geometry, meshing dominates FEM compute time, but with Monte Carlo, we get immediate feedback that can be progressively refined. In general, though, it's difficult to make an apples-to-apples comparison between a traditional PDE solver like FEM and walk-on spheres because they have very different characteristics. So in this example, for instance, FEM solves a Poisson equation pretty quickly once you have a mesh. Monte Carlo takes more integration time, but it also provides better spatial resolution with far less pre-computation. So overall, I think we should let go of this type of performance competition completely and instead focus on the fact that these are very different algorithms with very different potential use cases. Now, with that said, it is still worth identifying key challenges with current simulation pipelines. And whenever I speak to engineering folks who spend a lot of time with these simulation tools, generating sim-ready meshes is always brought up as the primary bottleneck. Now compare that with Monte Carlo algorithms like walk-on spheres, which open the door to progressive and view-dependent evaluation because, like path tracing, they're not bottlenecked by the quality of the discretization. So to stress test our solver, we modeled oxygen diffusion in a detailed model of the lungs by solving a Laplace equation with mixed Neumann and Dirichlet boundary conditions. Our walk-on stars solver allows us to inspect the solution easily on just a 2D slice, rather than needing to solve everywhere on the full 3D domain. If we instead try to generate a tetrahedral mesh for FEM quickly, then state-of-the-art meshing tools can end up throwing away important geometry like the trachea leading into the lungs. And to actually get the geometry right, we end up needing to wait more than 24 hours to generate a sim-ready mesh. Even in 2D, robust triangulation algorithms can fail to preserve geometric detail. But with Monte Carlo, we can operate directly, for instance, on the original Bezier representation to compute a diffusion curves image. So the main point here is that it doesn't really matter how fast or accurate your FEM solver is if mesh generation is slow and unreliable. Now, one could use adaptive mesh refinement to try to capture all the necessary details in an FEM solution. And to see if this argument holds up, here we consider the problem of heat radiating off infinitely many blackbody emitters, each with super detailed geometry and varying material coefficients. When we consider even just a single object in the scene, then we find that FEM cannot resolve either the original geometry or the details in the solution. Now, adaptive mesh refinement fixes this, but notice that we now need 8.5 million tetrahedra and 2.5 hours of meshing time, and that's just on a single model in this scene. With Monte Carlo, we can instead handle the entire scene without any kind of geometric pre-processing. Here's another example, not from a math or engineering book, but from a book on baking bread, where they say it would take extraordinary effort to represent such intricate, highly variable patterns in a heat transfer model. So we took this on as a challenge and used walk-on stars to simulate a piece of toast using a CT scan with about 4 million triangles. The simulation domain here is the narrow gap between the toast and the heating elements, including the little holes in the bread. So the first thing you notice right away is that conductive heat transfer that you get from walk-on stars is actually very different from radiative heat transfer you get from ray tracing. So if we want to make accurate predictions involving thermal transfer, then we really need good solvers for these second order equations. So we can use our solver to simulate how bread will brown under different conditions, and in fact you can do this faster than it takes to toast a real piece of bread. So the takeaway here is not necessarily about simulating food, but rather about making physical simulation more like rendering, both in terms of geometric complexity and rapid feedback. I would, for example, like to get feedback instantaneously if I change the shape or the size of the heating elements, rather than having to wait around to remesh my problem domain. We can also mix different physical phenomena. So here we have a lizard sunning itself on a rock, where the Dirichlet conditions provide the heat on the rock, and the Neumann conditions describe how much heat the lizard absorbs. And then the lizard can run walk on stars to make sure it's not going to be too hot or too cold. So in this example, we use a polygonal mesh to represent the lizard and a sign distance function for the rock. Also, to get our Dirichlet boundary conditions, we call a ray tracing algorithm on demand as a subroutine whenever we need to know the incident radiant flux density. There's absolutely no need to pre-compute this flux density over the entire domain ahead of time. So the takeaway here is that it's not only easy to mix and match different geometric representations, but also different algorithms. Now, physically informed neural networks, or PINs for short, have been getting a lot of attention these days for climate modeling. And I think it makes a lot of sense to fit neural networks to PDEs that describe highly nonlinear turbulent flows, especially if we have a lot of sensor data and can specialize to, say, the spherical geometry of the Earth. But I also think that the strength of frameworks like Monte Carlo and even FEM lies in their generality. They don't specialize to particular types of geometry, boundary conditions, or even PDEs. So, really, in my opinion, each solver has its own place, and they aren't quite perfect replacements for each other. For Monte Carlo PDE solvers, I would add that AI-powered denoisers make a lot of sense just like in rendering, because the solution to these problems is often quite regular. Finally, like any other numerical method, Monte Carlo PDE solvers are by no means a silver bullet. So like ray tracing, the biggest challenge with walk on stars is that walk lengths can become long in certain scenes, even though each step of the walk is usually big. And we don't at the moment have a principled Russian roulette strategy to terminate long walks. But like any other brute force Monte Carlo solver, there's still a lot of redundancy across walks. So to improve efficiency and reduce noise, our boundary value caching scheme instead takes walks only from the boundary and reuses estimates from these walks over the entire domain. This results, for instance, in much smoother streamlines in this example of a potential flow simulation in a wind tunnel. And what's also really nice is that we don't need a carefully prepared sim-ready mesh. We just run the analysis directly on a model built for visualization and design. Okay, so now I'll start to wrap up by mentioning some nice follow-up work by other research labs since our 2020 paper, which introduced the idea of the walk-on-spheres method to the graphics community. So with Monte Carlo methods, we have to deal with noise. So at EGSR last year, folks from Dartmouth presented a bidirectional formulation for walk-on-spheres, which reduces variance, and in principle, it can be made to work with Neumann boundary conditions as well. As already mentioned, we have a paper at SIGGRAPH this year, which adapts ideas from instant radiosity and virtual point light methods to reuse walks and improve efficiency. There's also a paper at EGSR this year, which shows how we can use the volumetric mean value relationship to reuse walks as well. I think a concrete next step to reduce variance even further is to find a way to unify the strengths of these three strategies into a single system. And I really think this is only the starting point. Compare this with path tracing, which has seen more than 30 years of research on variance reduction. There's also an exploration of the walk-on boundary method at SIGGRAPH this year, which provides richer boundary conditions compared to walk-on stars, but at the expense of higher variance. There's some really nice work on robustly performing geometric queries, such as ray intersections and closest points for neural implicit surfaces, which in turn lets you solve PDEs directly on neural implicits without needing to mesh them. There's nice work on solving PDEs in the exterior of a domain, which helps to do things like evaluate forces for molecular dynamics simulation. There's some preliminary work on applying existing algorithms for differentiable ray tracing directly to walk-on spheres for solving inverse problems involving PDE coefficients. And the goal here is not just to make walk-on spheres differentiable just for the sake of it, We have some very real inverse problems like electrical impedance tomography for medical imaging that require solving exactly the sort of equations we've been discussing today. At SIGGRAPH Asia last year, folks from the University of Waterloo used walk-on spheres as a subroutine to solve the Navier-Stokes equation in scenes with intricate and badly broken geometry. Now, we don't know if this fluid solver is going to replace all the other amazing fluid solvers we have today, but it's ambitious projects like these that make me think that building something like a ray tracer for physics isn't a totally crazy idea. I'm super excited about a paper on infrared imaging appearing at SIGGRAPH this year, because like that lizard example I showed earlier, this paper provides a unified Monte Carlo framework for simulating coupled physics. They use walk-on spheres for simulating thermal conduction and path tracing for thermal radiation. And what's really awesome about this is that we're building on top of existing path tracing technology to really go beyond graphics and rendering. And since we're rendering thermal images here, technologies like DLSS should apply out of the box. So I really think we should be on the lookout for many more such ways to combine path tracing and walk-on spheres. So for instance, recent differentiable ray tracing algorithms need to solve a Laplace equation with each ray bounds to avoid explicitly sampling visibility silhouettes. And I think it would be great to integrate walk-on spheres into more such algorithms. Beyond just physics and rendering, there are also many creative applications of PDEs in graphics and geometry processing, such as this fun example by Alec Jacobson on inflating surfaces from curves. Ryan Schmidt used walk-on spheres to do some agent path planning. So in this demo here, the ball follows the character moving around the scene by computing a smooth vector field locally at the center of the ball that points in the direction of the character. Okay, so lots of fun and exciting stuff, but we still need to answer many questions. So for instance, which other PDEs can we solve using walk-on spheres? Integral formulations are already known for important PDEs like the Helmholtz equation and linear elasticity, but we still need to develop estimators for these equations. Also, how can we extend these algorithms to other types of boundary conditions? So one big question in my mind is, well, what is the analog of a BRDF in our setting? Even with the caching schemes that I've already described, there's still a lot of redundancy both between and within walks. So how else can we share information to reduce noise without losing parallelism? Are there any high-dimensional problems that would benefit from walk-on spheres? And most importantly, for which applications does walk-on spheres offer unique benefits? So I think the wrong thing to do is to keep trying to solve the same problems that traditional solvers are well adapted to. We have a new toolkit here with very different numerical trade-offs. And in general, I really like this idea of simulating only what you see by augmenting path tracers with Monte Carlo PDE solvers, which hopefully one day will allow us to simulate physics that goes beyond light transport at the factory scale. And that's it. Thank you for listening.